Okay, so we had discussed about the upper yield point and the lower yield point in the previous class. So we'll take it out forward from there in the textbook. As the plastic deformation is continued, okay, beyond this yield point or the point after which you do not return to zero strain. So that's what plastic deformation is. As plastic deformation continued, the stress required to further plastic flow, termed as the flow strength, increases. Okay. So the stress which is required to further cause this plastic flow is called so plastic flow is what plastic deformation. So flow word is used in plasticity. What it essentially means is a plastic deformation. Okay. Similarly, you have something called a flow rule. Okay. So this just tells you how the stress varies with strain, how the deformation happens, and so on. Okay. Okay, so the flow strength rises, and this characteristic of the material in which further deformation requires an increase in the stress usually is referred to strain hardening. Remember, we have seen this word. Okay, so I mean, this is an example which you see over here, that as the plastic deformation is happening, the stress required to cause that is increasing, and hence this is the strain hardening. Okay, so this phenomena is observed in this particular curve. Okay, there are other parts of it which are not really useful for our course, so we will not discuss about this strain hardening any further than in this course. However, if sometime in the future you decide to take up uh, course in plasticity, then definitely you will be seeing lots of strain hardening over there. Okay, let's now move to figure 5.5c. Okay, so in figure 5.5c, that for glass, so this is for glass, and stress is proportional to strain up to the point of fracture. This is what you mean, stress is proportional with strain up till the point of fracture. So x represent fracture. Okay, its behavior is entirely elastic. There is no evidence of plastic deformation in either tension or compression. So even in tension, you end up somewhere over here and it ends. Okay, so that is how you have seen. So, sorry, I think the curve itself is missing, but the point is that it's a straight line curve, both in tension and compression for the glass. So its behavior is entirely analytic. There is no evidence of plasticity. Okay, so there is, even if you sort of decide to unload at this point, it will come back to zero strain. You decide to unload at this point, it will come back to zero strain. So there is no plasticity when it comes to glass. The stress at which fracture occurs is much greater in compression than in tension. That you can see, because for fracture to happen in compression you need a stress which is greater than 840 megapascals, and for tension it's quite less. Okay, maybe around 70, definitely less than 100 megapascals. So that is one difference. The stress at which fracture occurs is much greater in compression than in tension. This is a usual characteristic of brittle material, that the so-called fracture is fracture happens at a larger stress in compression than tension. So this is a usual characteristic of brittle materials, and glass is a very commonly known brittle material. Okay, so there are some specifics of glass like glass transition and things like that which we don't worry about at this stage, but by and large it's a brittle material, and that's what we want to know at this stage. So the stress at which okay, so now you also want to sort of see the viscoelastic behavior. For that you have to move to a different graph. Okay, so some materials exhibit a time dependent behavior as shown in 5.5D. Okay, so this is a time dependent material, and we'll see how that is. At room temperature, this viscoelastic material, remember we have seen this definition, it is a mixture of two behaviors. Can you recall them? Okay. At room temperature, this viscoelastic behavior is commonly found in polymers whose structure consists of long chain molecules with primary chemical bonds along the chain and secondary bonds between the chains. So you are well aware of how the molecular structure of a polymer is. Okay. So the secondary bonds can be broken by thermal activation. I mean, if you give it enough heat, the secondary bonds can be broken. I mean, there is an activation energy through which you have to overcome. So you are already aware of those ideas from your knowledge in chemistry. At higher temperature, metals can also exhibit time dependent effects. Okay. So we are not going to study that, but you should be aware that at higher temperature, metals which don't usually show a time dependent behavior, they are at its best plastic. Okay, which is time independent. Plasticity, which is time independent. At a very high temperatures, they can also start to show this viscoelasticity, which is time dependent. Okay, so for polymethyl methacrylate of this figure 5.5D, we note that the time effect is rather small. Changing the strain rate, this is the strain rate, and what do I mean by strain rate? You had the cylindrical specimen, the rate at which you were pulling these ends away from each other. Okay, that rate is dx by dt. Okay, so this is what the strain rate is. So remember, I mean if it's a uniform system, and if this is your initial gauge, so if this length is x, this dx by dt is what it is. Okay, so for a uniform case you can calculate it. Anyways, so you see that for the strain rate, you change the strain rate by a factor of 200 coming from here to here, and the stress only changes by 30%. Okay, so your graph in compression would go like this in this strain rate, and in a higher, very high strain rate, it would go like this. So the value of stress is not very different. I mean, it's 70 at one place, perhaps definitely less than 100 in this place. Okay, so the difference according to the author is not greater than 30 degree, and the same would apply in tension as well. Okay, so the difference is not much even when you change the strain rate at all for this material. In linear viscous liquids, on the other hand, a 30% change in stress would result from only a 30% change in the strain rate. So you should by this time know what a viscous liquid is, how the shear stress is related to the viscosity. Okay, so you must have done that experiment sometime in fluid mechanics also. I think you would have learned about it. There are two plates, and you sort of get this sort of a boundary layer because of the viscosity. So for such type of liquids, the sensitivity is quite high. I mean, you increase it by 30%, the stress will also change by 30%. So that is just to give you an idea that solids are definitely not fluids, which we already know. And at this time, you clearly know the difference between solids and fluids. The solids, a real and ideal solid is able to sustain a shear loading if you apply on it, and ideal fluid, which is not, there's no viscosity at all, it will not be able to sustain a shear loading, meaning it will collapse. Okay, so that is where you sort of end this discussion, and the effects of strain rate. And so this strain rate is definitely important in special cases, and there are people who work in high strain rates, like impact, when say when you hit a football with your foot, or a bullet strikes object, okay, say a steel, a vehicle, or a bulletproof, or any other structure. Those are problems in which the strain rate is very high. So that's where these behaviors will matter. So it doesn't depend just on the material, but also on the conditions that we have discussed. Sometimes the temperature, sometimes the strain rate, and so on. Okay. So unlike this case where the behavior, so gray cast iron is also a brittle material. Okay. Not as brittle perhaps, but definitely more brittle than the glass. So one of the differences you see is that the tension and compression behavior is very different for brittle materials, but for a ductile material that difference is very small. Okay, so for a ductile material, assume that tension and compression behavior is same. Okay, so you can just assume that they follow the same graph. I mean, on for example, look at other brittle materials like bone or rock, for example. I mean, try breaking a piece of brick, the construction bricks which you have, try breaking it in compression and try breaking it in tension. Okay, take a piece of chalk. Okay, try pushing them into compression and breaking it, and try pulling them out. It will always be easier to break them with a lesser stress in tension than in compression. So that's generally true for most brittle materials. Okay, so with this we sort of come to the next topic, which is idealization of stress strain curves. And most of this is something which you should be learning, that is at least the earlier discussions of this section you should be learning through machine design course, okay, and YouTube, or any other software like Microsoft, Yahoo, whatever service you would want to use. I'm not like propagating Google services anyways, but whatever works for you. So there are many terms which will come when you read this section 5.3, for which you should be looking at those videos just to get an idea of what they are. And I will demonstrate a couple of examples why you should do it. Please do keep in mind, despite the fact I am not discussing it in this class through this medium, you are expected to learn about them on your own. Okay, so please do that, and they will be coming up in some part or the other in our course. So please don't ignore it, and definitely don't leave it for the future, because the parts which come after this will very heavily depend on whether you have understood all this or not. Okay, so it will start, you will start feeling alienated if you don't follow it right away. Okay, so let's see what do I mean by learning by YouTube, and what do I mean by this idealization of stress strain curves. Let's come here. Okay, in any problem in mechanics of a deformable body, we need to know the physical relationship between stress and strain. Okay, I mean, that's the whole point of this entire chapter. The stress strain relation, together with the equilibrium equations and the strain displacement relations, must be satisfied at every point in a deformable solid. So this is the crux. At this point, you have the equilibrium equations. They are according to the book 4.13. Let's look at equation 4.13. Right. So you have equilibrium equations as equation 4.13. Okay. at this point in your solid. There is also strain displacement relations. Okay, this is something which we have studied earlier, so that is 4.33. Let's check whether that is the case. 4.33, yes, 4.33, equation 4.33. So, and then at the same point there must be a relationship between stress and strain. Okay, so you want to have all of it. Okay, you want to be able to write the equilibrium equations, which is in terms of stress. You want to be able to write the strain displacement relations, the relationship between strain and displacements, and the relation between stress and strain at this point of interest. And you should be able to do it practically for any point in this solid. Okay, so these relations for each differential element comprise the three steps. Okay, this was, remember, the first step of strain displacement, sorry, equation 2.1, the steps 2.1. The strain displacement relationship was about the display deformation in the compatibility equation, and the relation third was between force and deformation, in this case the relationship between stress and strain. So that is what is meant by each differential element. So any element which you cut out of this three-dimensional solid should follow these three steps. Okay, and then the solution must be based on these three steps. This we have been seeing, I mean, since the start of this course. Okay, from the foregoing discussion of the tensile test, we have discussed the tensile stress. It is evident that the different materials often have quite dissimilar stress strain relations, right? I mean, the glass was behaving in a different way that the steel was behaving, than the different way, say, the cast iron was behaving, than a different way the polymer was behaving. Okay, so the material behavior is very different. And with the exception of glass, no simple mathematical equation can fit the entire stress strain curve. Okay, so if you look at the equation 5.5, no simple equation can fit these curves other than glass. So glass we can easily fit by a linear relationship. Okay, but any other curve which you see, there is no simple curve which we can think of which will fit the stress versus strain behavior. Okay, so that is what is the meaning of this one. Now you want to find we wish the mathematical part of analysis to be as simple as possible, consistent with the physical reality. We will idealize the stress strain curves of figure 5.5 into forms which can be described by simple equations. So you see, you have these complicated graphs. Okay, you want to now make it slightly simple. Okay, not necessarily not necessarily a linear behavior, but definitely simple, and that is what is meant by idealization of these stress strain curves. Okay, so that is something which we would want to do. And all of these curves which you look over here, they are idealizations, and they are very easy to write mathematically. Okay, the stress versus strain can be very easily written mathematically. That's the point. Okay, so whether we can actually idealize a stress strain, a complicated stress strain curve into one of them, will actually depend on how small your strain is. Okay, if the strain is very small, you can make many of these idealizations. Okay, and so at what strain you are, I mean, if you are at a very large strain, perhaps it is easier to assume some other thing. If you are at a very small strain, perhaps it is easier to assume a linear behavior. So we will see that, okay, how those approximations work. Okay, now there are examples which you have now in the next paragraph, and this is where your job sort of begins over here. Okay, so example, sometimes we must design structures so as to accommodate or produce certain desired deformations. So you want some parts of your machine to deform in the way you like it for the machine to work. So think of a this pen which has this spring at the top, and you press it and the nib comes out, and you write, and then you press it back and the nib comes up. So you want the spring to deform to a certain degree and then to undeform it back. Okay, so that's, you want a deformation, you want a controlled deformation. So that's one example of the design of springs is one way. Okay, a certain load should produce a given deformation. Then you have safety valves. This is where your YouTube journey should begin. Then you have bumpers in a car. Okay, crash panels, and many other things. You want all of them to deform, but not deform as much as they want to, deform only to a certain value, so that those things can serve the purpose they are supposed to serve. Okay, like for example, the bumper of a car must deform slightly. Okay, I mean, it should not immediately break as soon as a small force is applied. At the same time, it cannot just deform for a very large amount of to a very large amount. Okay, because there are other parts of the car as well. So you have to see the use of all of these and the ones which are mentioned in your book, so that you can learn about these things. Okay, then there is a description of where the solid mechanics acts beyond this, and all of them will require you to do this. For a given amount of stress, what should be the strain which should be produced? Okay, so that is what you would want. Now, for a given amount of stress, we want a specified range of deformation in which these things should be deformed. Think of some other manufacturing process like forming, metal forming, okay, or cutting. These are other manufacturing process. Some of these experiments you may have done in your workshop practice course. So the strains have to be are usually small compared to one, and then there is a spring back effect. So when you form metal sheets, you should look at what of metal forming process is first of all, if you're not clear. Okay, and I'm sure there would be some course in production engineering in your degree which will teach you it in much greater detail. But the purpose here is for me to be able to tell you that mechanics acts in all those places, in manufacturing and design both. Okay, so metal forming, you should look and see if there's a risk of spring back, just like the paper which you had would unfold itself. So there is a spring back effect as well, and that is a problem because you don't want that to happen in a metal forming process. In metal cutting, the strains may be even greater than unity, and then there is a plastic process with which the strains are so high that there is plasticity and the failure has happened, and then you are able to cut the material and the chips are gone away, are taken away. So that's how you use mechanics in the material process. So please check the metal cutting process as well. Okay. Okay, so we do not want excessive deformation. We want the deformation to happen in a specific place. So please read this paragraph. Okay, there are a few more discussions in these paragraphs, and we'll sort of come back to where we had left, that of our need to so there's also this word of wear. So you must have word wear and tear. Okay, the sole of your shoe or your sandals wears out after a while. Okay, and then you must replace them. So mechanics acts in wear as well. So there is a small description in your paragraphs. Please read it and see how wear works in machine parts. I mean, the ball bearings which you use in the sprockets of your cycle, when you get your bicycles serviced, they will replace those ball bearings. Okay, because they get worn out. That is what wear is, because of the friction. So they act as a they act due to this rolling friction. Okay, where the friction has to be reduced for the parts in contact. Anyways, so we'll come back to what we had in the sense idealization of these uh, stress strain behaviors. And one thing which I'll repeat again, most of your materials around us won't ever have a stress strain behavior like this. Almost all of them will not have a stress strain behavior like this. Okay, they will have something more complicated. We want to idealize them into something simpler. Okay, that's what we are trying to do. Okay, so you have these 6 idealizations given. Okay, and the first one is clearly a rigid material. You have known this material all along. This material does not deform. Okay, a rigid material ideally, okay, that's why it's called an idealization. It's very unlikely that you will ever find a material which never deforms under whatever amount of load, but that's why you call it an idealization. But that's what the graph will look like, that the stress will keep on increasing to whatever value you want, but the strain will be 0. Okay, so this is one in which no strain regardless of the applied stress. This idealization is useful in studying the gross motions and forces on machine parts to provide for adequate power and for resistance to wear. So where like for example, when you, I mean, I don't know if you will actually study the design of ball bearings. Okay, in this one you don't really assume that these spheres which you have will undergo any deformation. All you consider is the wearing off at the edges. Okay, and the rest of the part is assumed to be rigid. So that is one of the things which you do, and then there are other several parts where you have to assume, or it is reasonable to assume, that your body solid is rigid. Okay. Okay, then you have a linear elastic material in which the linear elastic material in which the strain is proportional to the stress. I mean, you look at this, and this idealization is useful when we are designing small deformations. Okay, so this is especially good for small deformations. So if you have a piece of metal, okay, and you have seen the graphs in figure 5.5 before, clearly they don't look like this. Okay, they look very different from this. But if your strains are small, okay, if you have very small deformations, I mean, you don't go to the higher strain values, you stick to parts which are let's see, okay, you stick to parts, say somewhere until here for this curve. Okay, it is reasonable to assume that this particular part is actually linear elastic. Okay, so this is what is meant by idealization. Okay, so we want to normally design this for fatigue or failure in brittle structures. So brittle structures, as you know, I mean, given in your textbook for say a glass, you want to design for or prevent a fracture. Well, the easiest way is to assume this linear behavior and then be within this region. Okay, be under this, and then you will be safe. It will not fracture. Okay, then you can have a perfectly plastic material. Let's see. Okay, so it's called a rigid plastic. So let's see. A rigid plastic material is one in which the elastic and time dependent deformations are neglected. Okay, so why is it called a rigid plastic material? Well, there's a rigid part. Okay, look at this, that's definitely there, and then there is a plastic part. Okay, so this is the plastic part, and As soon as you say it's a rigid plastic material, then you have to ignore the time dependent. So it is time independent, because plasticity is time independent. Okay, so these are time independent, and this is an idealization which you make. If the stress is released, the deformation remains as they are. Obviously, that is expected of any, like if you remove the stress, whatever it is, this you will not have a zero strain. Okay, so you will have a non-zero. So that's the characteristic of a plasticity. Strain hardening may be neglected. Okay, so if you ignore the, so you see there is a rigid perfectly plastic material, so this is non-straining and this is strain hardening. So we had discussed strain hardening. Strain hardening was the case where to cause the more plastic deformation, you must keep on increasing the stress. So that was strain hardening. There is another possibility of a rigid plastic material, or so-called perfectly plastic material. In this case, there is no strain hardening. I mean, to cause a plastic deformation, the stress need not be increased, but it is still plastic in the sense if you unload from here, it will not go back to here. Okay, you will end up somewhere over here. Okay, so that is the difference between strain hardening and a non-strain hardening plastic behavior, idealized plastic behavior. So this is called actually a I mean, even this is a rigid plastic material, okay, but we call it perfectly plastic because clearly there is a rigid part of it. So you keep on increasing the stress, no deformation will happen, and after a certain value of stress is reached, it will start to plastically deform over here like this without strain hardening, and in this case with strain hardening. So both of them are technically rigid plastic, but one of them has strain hardening, the other has a non-strain hardening. So you can remember in whichever way you would want this to happen. Okay, so many of the machine and the metal forming machining process and the metal forming process, I mean, you may have done this turning operation on a lathe. Okay, if you have not done or you have forgotten somehow in an year, please look it up in your videos, online videos. Okay, so what is a turning operation on a lathe? I mean, all of them require you to reach a stage where maximum load can be taken so that fracture can eventually happen. Okay, so that's where you would want fracture to happen. Okay, and similarly, I mean, a metal forming process is in which you have to take maximum loads to cause a certain amount of deformation, the desired amount of deformation. Let's come back to the elastic plastic deformation. So these are the again, so do keep in mind, it is not materials which are rigid or linear elastic or rigid plastic. Okay, it is their idealization which is either rigid or linear elastic or rigid plastic and so on. Okay, so this is what you have to know. So elastic plastic, just like rigid plastic, there is a linear elastic part and then there is a plastic part. Okay, so and this is also an elastic plastic one in which there is a strain hardening. There was no strain hardening over here. Okay, so what I mean is, in reality the stress strain curve may look something like this. Okay, but you can idealize it as a elastic perfect plastic material, this black line which you see. Similarly, in this case, your actual stress strain graph may look something like this. Okay, and as you know, this is a very complicated stress versus strain graph, this is a very complicated stress versus strain graph, but you can idealize them as this elastic plastic strain hardening kind of a material. Okay, so you will sort of reduce this complication and the mathematical treatment involved by making these idealization. So that is what we mean. There is no material which is actually elastic plastic. You fit that complicated one into your idealization, and that all judgment depends on you as the user of these things. Okay, Now let's come to figure this example 5.1. So there are two coaxial tubes. So, okay, this is example 5.1 of your textbook. There are two coaxial tubes. The inner one of a 1020 cold rolled steel. Okay, so this is the inner one, inner tube, and clearly it's a coaxial, so the axis is somewhere over here. It's the same for both the tubes, and this tube is the outer tube, which is aluminum. So this has a cross section of AS steel. This has the cross section AA of aluminum, the outer tube, and the cross section and the area is given. Okay, they are compressed between heavy flat end plates. So these are heavy flat ends and plates. We wish to determine the load deflection curve of the assembly, of the overall assembly now. Okay, we are not looking at the load deflection curve of the steel or the aluminum tube. And this we wish to determine load deflection of the assembly as it is compressed into the plastic region by an axial force. Okay, so this is compressed into plastic region by an axial force, capital P. Okay, so let's start with this problem. Let me just pull this one over here. So please notice the way we are dealing with this problem. Okay, the way we are approaching this problem. The objective is to find the load displacement behavior of this entire assembly of two tubes. Okay, so there are two parts of it, and you want to find the load displacement for the entire assemblies. So you must have done all these parts in assembly in one of your earlier courses. I think technical drawing, engineering drawing, whatever you call it. Okay. Now you consider a symmetrical loading, and that's shown in figure 5.9. Okay, so the top plate you are applying a force P, and same force would automatically get applied at the bottom, compression. The steel one, because you are compressing, it will apply this force on the plates in this direction, both the aluminum and the steel plates, and you are assuming a symmetrical case. So all the force which acts, say, from this, okay, because of the symmetry we assume that all of that acts in the center for both the tubes. And then you draw the model of the steel tube. Okay, so you already know in from your experience that this dashed line means a hidden sort of a profile. Okay, so the outer profile is solid line that you can see, the inner one is hidden. Okay, and then this force applied on this steel tube is Fs. Again it is applied on the center because of the symmetry, and that is equal to As into sigma s, where sigma s is the stress on the steel tube. Okay, the deformation in the steel tube is delta S. Similarly, for the aluminum one, you have AA and sigma A and delta A. So these are the idealized sort of models for the three things involved in this assembly. And we want to now apply the stress strain relationship and find out the uh, load deformation curve. And we already have a load P, we already have this unknown delta, and our objective is somehow to find the relationship between P and delta in terms of what we have in front of us over here and over here. So one of the things to note is that you want to find this as it is compressed into the plastic region. So there is a specific stage which is given to you, as it is compressed into plastic region. So let's see how this works out in our problem. So let's start with the steps 2.1 and we'll slightly jumble the order which we have done several times in our problems, just because one part is easier, the other is harder. So we always start with the easier thing first so that we get more confident. So geometric compatibility here is the easiest one. Okay, so we write that the strain in the steel tube is the same as the strain in the aluminum tube. How can we write that? Well, the original length is the same of both the tubes, and since both of them are deforming by this delta S and delta A, and those values have to be the same, that's why this is such that delta S is equal to delta A. Okay, and if you divide it by the length of the steel and length of the aluminum, they are the same. So that's why you are able to write ES is equal to EA. So we are writing this as equal to E, which is the strain of the assembly, and this is equal to delta by L. Okay, so we ignore the this particular thickness is ignored over here. Okay, the thickness of these, and it's not given, I think, anywhere that they are thick. So it's reasonable to ignore these. They are told that they are heavy, but heavy does not mean they have to be thick. I mean, they can be of a very high density, so we don't know. Okay, so this thickness is ignored when we write this L. So this L is written for this steel and the aluminum tubes. So that's the geometric compatibility. Look at the stress strain relation. So this is the objective. You want to start from zero, take it to the elastic region, which it will automatically, and it will just come into the plastic. And this should happen when both the materials, both the steel and the aluminum, are actually in the plastic region. So let's look at figure 5.5a and b to look at the curve of 1020 CR and 2024T4. So let's look at 5.5a. Okay, so let me just rub this part out, make it slightly more legible. Okay, so this is our steel. Okay, 1020 CR steel, and look at its curve. This is this dashed line, goes all the way. Okay, now this is for 1020 CR. Now is it okay? I mean, so this obviously this curve is quite complicated, but is it reasonable if I idealize this behavior as this, which is elastic plastic without strain hardening? Okay, so this is an idealization I would want to make. Now let's go to 2024T4. It is this figure. Just enlarge it so that you can see it. Okay, so this is the aluminum material, and you see the behavior of this one. Well, it's something like this. Okay, and it's showing some sort of a increase, but not so much. Okay, there is seems to be some increase, but not a lot. Okay, now looking at both of these two curves, so this particular one also, I mean, this is a complicated part, so let me just idealize it like this. Okay, so both of them I have assumed, or I have idealized as an elastic plastic stress strain behavior, and that will help me solve this problem. Okay, so see, okay. So this is shown in figure 5.20, these idealizations. So this is for the steel, this is for the aluminum, okay? And you might question, how have I found out this 590, which is the yield strength of aluminum, and 380 mn per meter square for the aluminum. Okay, so the way to see this is again from either from a table somewhere or this diagram itself. So let's look at 1020 CR. So you have this particular point as 0.02, and this must, this 0.02, remember how the yield strength was calculated? So you take this line, and then wherever it intersects with over here, this is the yield strength. So this is the point I have found out, and that point has come out to be 590 mn per meter square. How do you have to do it in reality? Well, you have to actually draw a curve like this. Okay, you have to draw this line with the same slope as the initial elastic part, and maybe using a set square if you would want, and then draw this and then draw another line. So you should be using set squares if you are not sure about how to use them. I think at some point you must have used. So that's how you would get this value of 590, and similarly for 380 for this one. Okay, so this is 0.02, and you keep this up, and this will go to 380. So that's how I know that this curve is there. So I know the behavior, but now I have quantified it. So as soon as 590 is reached, I will assume this non-strain hardening plasticity in both the cases. Okay, 590 and 380 approximately. So this is the idealized behavior which I have. And so let's start in the region. So let's start, because there are two separate regions, one elastic, one plastic. So let's start with one part. So the strain is between 0.0032. Why is this important? Because at this value, the yield strength of the steel is reached. Okay, so that's why I have first considered this interval. In this interval, one good point is that both the steel and the aluminum are behaving linearly. Okay, like this. So in this case, and in this region, sigma s is equal to es into s and es into e. Okay, so epsilon s is the same as epsilon because of this condition, geometric compatibility. And for the aluminum as well, you would have ea into epsilon a equal to ea into epsilon. Same logic. So you can find with this what es would be. So you in this region you already know the Young's modulus. Okay, sorry, you would not know. So you know the value of stress, you know the value of strain, and hence you can find es. Similarly, you know the value of stress, which is 380 divided by the strain, which is 0.0032. Okay, so 590 divided by 0.0032, and you would have that done. Okay, so that's the first part. And how would you find it for the aluminum? I mean, it's not, I mean, if you don't want to look, if this triangle is harder to solve for the aluminum, you can always pick up this triangle. The slope will remain the same, right? So that is how they have written it as 380 divided by 0.005. Okay, so the Young's modulus, the elasticity modulus has been found out for both steel and aluminum. Okay, now we take the second range, which is between 0.0032 to 0.005. Okay, this one. In this region, sigma s for the steel, well, for steel it would be equal to 590. Okay, look at this one. So it's constant now. Okay, and mn per meter square, and for aluminum it would be ea into epsilon a. Okay, and this would be ea into epsilon. This is the same as this. So you know this ea, you already know this maximum value, so sigma is already known at this place. Now in the last range, which is in the plastic region, okay, what is that range? 0.005 greater than E. So in this region, the steel will have a stress of again 590 because it's constant. So we are referring to, say, a strain over here which is greater than 0.005. So this case it will be 590 mn per meter square, and sigma A will also be the yield strength, that would be 380. Why is this happening? Because of the idealization which you have taken. So you have these three different ranges of strain, and you can easily find out what the stress values are. Okay, now if you look at the top plate over here, this plate, you write the force balance, that would be sigma s into as plus sigma a into aa minus p is equal to 0. Okay, and that has to happen irrespective of in which range you are. So sigma s, whatever is in that range, you will get that. Okay, now the final part is how to draw the load versus displacement deformation for this entire assembly. Quite simple. What is delta? That is L into E. Okay, so this has three intervals, you see, 1, 2 and 3. So you should create these three intervals, 1, 2 and the third one, in delta. So with E value, you just divide multiply this E with L, and you will get this interval 1, 2 and 3 on delta. And similarly this P you can find from over here, so that will be equal to sigma as plus sigma SAS plus sigma AAA. And every time, so you all have the, in the first range you know what sigma S is, you know what AS is, you know what sigma A is, you know what AA is, so you will be able to easily find what this will be. Okay, so this is how you should be able to get your final value. Okay, so it is increasing from 0, the deformation of this entire assembly, and going into this uh, non-strain hardening plasticity. So this is how you can study the plasticity of an entire assembly with the plasticity of the individual parts. So very useful. I mean, if you have one part which has failed, one is safe, how does the whole assembly behave? Okay, so this is how most machines will have this challenge. Okay, so we stop this class over here, and in the next class we'll understand how the elastic stress strain relationships can be developed, and that's where we get down to the business of mathematics. Thank you.